Okay, guys, and moving into the second part here of our notes in 6.2, we talked about solids along the axis, pyramids and cones being one of the three-dimensional solids we can create and measure here. Now we're moving on into the second part, solids on the plane. Okay, so there's not really a whole lot of prep work that needs to be done here. We're just going to dive into our first problem. So what's going on here, guys? Let's read it together. And sorry, the iPad is printing some weird stuff here, so let's just ignore that. Okay, so actually, does that work if I erase? Oh, that did work. How about that? They say that works for getting a dry erase Sharpie off a dry erase board. Anyway, here we go. The base of a solid is the circle x squared plus y squared is equal to 4. And its cross sections now are squares that are perpendicular to the x-axis. We're going to find the volume of this solid. I don't expect that to make any sense to you guys here at all. So let me try to explain this as carefully as I can here for what's happening. In a solid on the plane problem like this, I want you to think about construction. And I want you to think about building a really large structure. And probably the first thing you would do, whether you were building the Convocation Center at NIU or DeKalb High School, is the first thing you'd do is you would level some ground and you would pour a foundation, most likely out of concrete. And that's effectively what's happening right here. The base of the solid that we're about to draw is a circle, x squared plus y squared equals 4. So what we're going to do is we're going to pour concrete in that shape right there. So let's draw this. I'm actually going to be drawing two different pictures right here, two different graphs. All right, and the first one I'm going to do is a really nice and simple, that's not what I wanted that to be black. A really nice and simple straight on view of what's happening. Now, since I just painted the picture here of construction and the Convocation Center or DeKalb High School, imagine now that you are flying in a helicopter up above the ground and you're looking straight down. Here's your x-axis. Here's your y-axis, okay? Or, more to the point of what we're doing right here, maybe that x-axis would be a straight east-west line and your y-axis would be a straight north-south line. So we are going to mark off our area here and we're going to pour concrete in the shape of the circle x squared plus y squared equals 4. And what I'm hoping you guys know, the center of that circle is going to be at the origin because there is no h and k. And remember, guys, that this number over here is actually r squared. If your radius squared is equal to 4, that means that your radius is equal to 2. So we are going to pour concrete in the shape of a circle centered at the origin with a radius of 2. So imagine now that we've cleared this out and this entire region right here is our concrete pad, our foundation. And once we get that circular concrete foundation laid and dried and cured and we give it enough time so it doesn't crack and all that stuff, then we can build almost anything we want off of that. But coming up with that foundation first is really, really important. So we've done that, okay? It's been a few days or weeks or months or whatever, and we've got our concrete poured. Now what we're ready to do is to start building up off of this surface up into the air. So again, if we're up above this in a helicopter right now, we're not really going to be able to see what's happening here because it's coming straight up at us. But right now, guys, the concrete is two-dimensional. It's flat. It exists in the XY plane. We now need to build something up off the ground in the Z direction to give this thing some volume. So to draw that, this is going to look very, very different. And this requires kind of a different line of thinking than you guys are probably used to. And some of you guys are going to pick this up right away, and some of you are really going to struggle. But we got to practice this. So watch what I'm going to draw over here. Okay, nothing fancy right now. There's another x-axis. But now some of you are not going to like what I'm going to do next. This slanty line right over here, that is your y-axis. And that means, everybody, that from that point of intersection, the origin, the z-axis is pointing straight up into the air like this. Okay, so now it's like maybe we're in our helicopter still. It looks like we're up above the XY plane, but we're way off to the side and we're not directly above the foundation and the structure. We're somewhere else looking at it. Now, here's one other thing you're not going to like. You see that pretty blue circle that I drew here on the left? I'm going to draw the exact same thing on the right. It intersects the y-axis here, and then the same distance down, because of course all radii of a circle are congruent, and it intersects the x-axis in pretty much the exact same way right about here and right about here. So this circle isn't going to look like a circle now that I'm way off to the side. It's going to look, everybody, a little something like this, okay? And then if we draw it there and there, that's about what that blue circle is now going to look like now that we're way off to the side. It's still a circle, but now it just looks like an ellipse, an oval right there, because our perspective is skewed a little bit. That's okay. That's where we have, and that's still our concrete pad. Now, the question is, and this is different on every problem, what are we building coming out of this concrete pad? And if I read a little further in the problem, I'm building a three-dimensional solid whose cross-sections are all going to be squares perpendicular to the x-axis. And we're supposed to find the volume of that solid. So we're actually going to draw just one of these cross-sections. Now, you might know the answer to this already. How many of those cross-sections are we actually going to be making to draw this three-dimensional solid? The answer to that is infinitely many. But of course, we can't actually draw that many. We're just going to draw one. So I'm going to draw a square, everybody, that sticks up in the air in the z-axis direction that runs perpendicular to the x-axis. Okay, so perpendicular to the x-axis would be a line segment that looks something like this. And if you guys remember your vocab from geometry, that line segment right there, whose endpoints are both located on a circle, that's called a chord. And what I've drawn in red right there, guys, that one red chord is the base, the bottom side of one square that's going to be sticking up, straight up in the air, coming out of this concrete pad. Now I'm going to draw the exact same red chord over here in this figure on the right. Now, perpendicularity doesn't translate well to when you're drawing something in three-dimensional space. My point here is that the x and the y-axis, of course, are perpendicular. And guess what? Now, you're really not going to like this. That is still a right angle, because the x and the y-axes are still perpendicular, but it sure doesn't look perpendicular, kind of for the same reason that our circle now looks like an oval. So perpendicularity doesn't translate well into a 3D perspective. But you know what does? Parallelism. That red line segment that we drew on the left, yeah, it was perpendicular to the x-axis, but it's parallel to the y-axis. So now when I go over here on the right, I'm going to draw this red segment yet again, and I'm drawing it parallel, or as close as I can, to the y-axis. Okay, so that segment right there in red is meant to mimic this same segment over here that I drew on the left. And now this might start to make a little bit more sense, because now I think you guys can see what I'm about to do. From that red line segment, we are now going to draw a square sticking straight up in the air off of that one piece, looking something like this. So that one big red square that I drew is sticking straight up off of the XY plane in the Z direction, and it's standing up in the air. And of course, there are more. Don't bother trying to draw these guys, but guess what? There's one right here, and there's one, I don't know, right about here. And there's an infinite number of these squares, and when you put them all together, you're going to create a three-dimensional solid. But it gets really, really messy to try to draw too many of those, so we're probably better off just dealing with one. Now remember, everybody, we're following the same volume formula in every one of these problems we do. And what we need to do is come up with our formula here for A of x, the area of one of those squares expressed as a function of its x-coordinate. So let's talk about how to do that. Let me go back over to my first diagram right over here on the left. Now that red segment that I drew is a chord, but ask yourself, what does it represent in terms of the cross-section that I can see a little bit better over here in figure 2? Well, this segment right here is the base of a square, or it's one side of the square. So this distance right over here, I'm going to call S for side of a square. And of course, it's the same distance right over here. And what we're going to need to do, and I think that diagram 1 is the better spot to look for this. Humor me for just a second here, guys. Let me put a little line there. All right. So if we go back to figure number 1, we've got to try to come up with a way to represent S as a function of x. So how do we measure the length of a vertical line segment? We take the top function here minus the bottom function. Okay, what stops that red line segment on the top? That would be the top of the circle. And what stops it on the bottom? The bottom of the circle. Now, this is a little bit tricky here. I'm going to switch to green for just a second. Remember that the equation of the circle, everybody, was x squared. Uh-oh, I lost it. Come on now. X squared plus y squared was equal to 4. Since this is going to be a dx problem, we'll talk more about that later, I want to solve this for y. So we're going to get y squared is equal to a 4 minus x squared. And we'll take the square root of the left and the square root of the entire right side. You can't do that term by term, everybody. And we're going to get y equals plus or minus the square root of 4 minus x squared. And remember with that plus or minus, that actually means that the circle is two different functions. The top function is y equals the positive square root of 4 minus x squared. In fact, I'm going to write that right here. Y equals the square root of 4 minus x squared. And the bottom function, this one right here, is the opposite of that. Y is the opposite of the square root of 4 minus x squared. So, when we go to figure out how long S is, which is not constant, it's going to be different depending on your x coordinate here, S is the top function minus the bottom function. The top function is the square root of 4 minus x squared, minus the bottom function, which is the opposite of the square root of 4 minus x squared. And that means that S, let's run with just, here we go. Just S here is going to be 2 times the square root of 4 minus x squared. Okay, that is the length of S, and it's going to change depending on the x coordinate where you draw it. But it's not a bad idea to just double check that idea real quick. Like for example, let's do the easiest one. Right here, guys, when your x coordinate is 0, how long, not what I wanted to do, Mr. Fontana, when your x coordinate is 0, how long is that chord? Well, it should be 4, right, guys? Because that's a circle with a radius of 2, so let's check it. When you put a 0 in here for x, 4 minus 0 squared is 4, the square root of 4 is 2, and 2 times 2 is 4. It seems to work there. Here's another weird case. How about over here where x is 2? How long will that chord be? Well, the chord doesn't actually exist there. The length of the chord should be 0 when x is 2. And let's try that. 2 squared is 4. 4 minus 4 is 0. The square root of 0 is 0. And 2 times 0 is 0. So I feel pretty good about that formula right there for S. That is the length of one side of your square. Where are we going with that? Now, we've got to come up with a formula for the area of your cross-section. So ask yourself this question, and it'll change from problem to problem. What shape is our cross-section? Well, in this problem, just like in the example we did in that pyramid a while ago, we are dealing with square cross-sections. And the formula for area of a square is side squared. Right over here, we've got the formula for S as a function of x. So A as a function of x is going to be your side length, which we just found to be 2 times the square root of 4 minus x squared squared. And you know what? That can be cleaned up a little bit. So let's see what we can't do to make that easier to work with then. So a of x is going to be, and remember guys, you have two factors here, this one and this one. Each one of those factors needs to get squared. So the 2 squared is going to give you a 4, and then the square root of 4 minus x squared squared is going to be 4 minus x squared. And given what's coming next and the fact that this isn't difficult to do, nope, I lied. I was going to distribute that, then I just thought better of it. You'll see why in just a second. And hey everybody, look at what we just came up with. We now have our formula for a of x. From here, the rest of this problem is pretty easy. Volume of a three-dimensional solid is always the integral from a to b of your cross-sectional area formula, a of x, taken with respect to x. So let's fill in what we know now. Volume is going to be a definite integral of, and here we go. Your cross-sectional area formula is right here, and what I realized just a second ago, guys, better than distributing the 4 out in front, I'm going to pull that 4 to the beginning of that integral using the constant multiple rule, and then the integrand is just going to be a 4 minus x squared. Much easier to deal with right there. Okay, so there is a of x. We're integrating all this with respect to x, and the limits of integration now need to be the lowest and highest values of x. So as we go back and we look at what this region looks like, probably figure number 1 is the best spot for you to see that this thing begins at an x value of -2 and ends at an x value of +2. So what we definitely could do, everybody, although don't write this down just yet, is do the integral here from -2 to +2, and that will work. But one of the things we really want to get in the habit of doing here in this particular section is taking advantage of symmetry anytime it exists. And what I think you guys are going to realize pretty quickly by looking at figure 1, this concrete pad that we've poured is perfectly symmetrical. If we found the area, or I should say the volume of just half this figure, and then simply doubled it, that would get us the right answer, and that would be a lot faster and easier. So what I'm going to do instead, you guys, is only do the integral now of the right half of this region from 0 to 2 and simply double the result that we're going to come up with there. Now, the point here is, everybody, 0 by far is the easiest limit of integration to use. Anytime you can use 0, you should try to do that. So where does this get us now, guys? Volume is equal to 8 times, all right, here we go. Antiderivative of 4 is going to be a 4x minus the x squared becomes a 1/3 x cubed. And we're evaluating all of that from 0 to 2. So let's see where that gets us. So volume then is equal to 8 times, and here we go. Plugging in a 2, 4 times 2 is going to be an 8, minus, well, that doesn't work out great. 1/3 times 8 is just going to be an 8/3. That's what you get from the 2. Minus, let's not assume, but let's find out. Yeah, when you plug in a 0, you get 0 minus 0, so sure enough, that's just going to be 0. Ugh, so what does that do for us here, guys? The 8 minus 8/3, this is actually 24/3 right there, so that is going to become an 8 multiplied now by a 16/3, and the 8 times 16, oh, I don't know, 8 times 8 is 64, so if I double that, 128/3. I don't believe we put any units in this problem. We did not inches, feet, miles, anything like that. So our answer here, everybody, is just going to be 128, and we're just going to put cubic units for the answer to this problem. And unfortunately, you guys, there's not any geometric formula we can do to come up with this volume to verify it, so I'm going to ask you guys to trust me on this one. So that is a pretty significant amount of work here for problem 3a, but this is a way we can apply the same concept that we were talking about a while ago. This formula right here for volume of any three-dimensional solid, and we can apply it to a setting here where we're building a solid coming off the plane. If you're thinking, wow, that was a lot of work and it took a lot of time just to do one problem, you're right. And I'd like to promise you they're going to get a little bit quicker, a little bit faster and easier the more we do, and they will to an extent, but these are not ever really going to be easy problems. Okay, I want to do two more variations on this problem here. So let's take a look at what's going on here in example, what is this, 3b, 4b? I don't even know where we are. This is 3. Okay, here we go. So example 3b. So the base of a solid is the same as it was in A. Okay, that's good news, everybody. So imagine, we poured a concrete foundation, we built something out of wood, and eventually it burned down. But the concrete is still there. So now we've got the same foundation, the same footprint, but we're going to build something a little bit different. Now, its cross-sections are semicircles, perpendicular to the x-axis. And we're going to find the volume of this solid. Okay, guys, so we're going to try to draw the same things we did before, okay? We're going to draw a straightforward, nope, not like that. We're going to draw a straightforward XY axis, and I'll call this figure 1 again. And then eventually, we'll draw our 3D graph right over here on the side, looking something like that for figure number 2. But I'm getting ahead of myself. So, up in the helicopter, directly above, we draw the same circular concrete footprint that we had before, and that's still the function x squared plus y squared is equal to 4. And now when I draw that over here, it still looks exactly the same. It still doesn't really look like a circle, but it is. And our cross-sections are still running perpendicular to the x-axis just like they were before. So I'm going to draw, not very well, I'm going to draw this red segment right here and try to draw the same thing happening right over here, again parallel to the y-axis. Now, the only thing that's different right now is that in the previous example when we looked at it, I called that piece S. And the reason I called it S was because that was the side of a square. But in this problem, we're creating something different. Now, as I read in the second line of this problem, the cross-sections are semicircles. Oh, so okay, instead of this red segment being the base of a square, now it's going to be a semicircle that kind of sticks up in the air and looks like this. So my question for you guys is, this red piece down here, what do you call that piece right there in a semicircle? Answer to that, that's your diameter. So this same piece that I called B in the previous problem, it's the same thing now, I'm just going to call it D. But the good news is, its measurement hasn't changed. D is still going to be top function minus bottom function, which if I'm not mistaken was 2 multiplied by the square root of 4 minus x squared. Let me double check that. That's what we got for S, I believe, in the previous problem. Yep, right here. Okay, S was equal to 2 times the square root of 4 minus x squared. Same thing here for D in this problem. Okay, now if I'm kind of thinking ahead, over here, we're going to try to come up with the formula for area of one of those cross-sections. And the formula for the area of a semicircle, everybody, let's think about that. Formula for area of an entire circle is pi times the radius squared. This is going to be half of that. 1/2 times pi times your radius squared. Now that right there tells me something important. If I want to know the area of a semicircle, I need to know its radius. And what we have over here is diameter. So if I want to come up with a formula for radius, that is going to be 1/2 multiplied by your diameter, 2 times the square root of 4 minus x squared. And conveniently, what happens here? The 1/2 and the 2 cancel. So your radius is just going to be the square root of 4 minus x squared. And I can now put that right over here to get a formula for area as a function of x. That is going to be 1/2 times pi times your radius, which is the square root of 4 minus x squared, squared. Oh, and how pretty is this? Now I have a square root being squared, so a of x is going to clean up very nicely now to become a 1/2 times pi times the quantity of 4 minus x squared. Could we do something else here? Could we distribute the 1/2 pi? Yes, we could. But as I'm hoping you saw and you learned from what I almost did in the last problem, that's not really going to help us at all. So I'm going to leave it in factored form like this. So now that we know our a of x formula, that's not what I wanted. Now that we know our a of x formula right here, we're ready to go to our volume expression. Volume is equal to a definite integral now of your a of x function, which is going to be a 1/2 pi times 4 minus x squared. I'm going to pull out the constants here, the 1/2 pi, which I'm just going to make a pi over 2 out in front there if you don't mind. So the pi over 2 comes out. The 4 minus x squared stays in the integrand. We're integrating with respect to x. And the limits of integration are, again, the lowest and highest values of x in this region. Well, it's the exact same conversation we had before, guys. This goes from -2 to +2, so you could use those for your limits of integration. But instead, we're going to do the integral just from 0 to 2, and then we are going to double that result. Much faster to do it that way. So, volume equals that 2 and that 2 on the bottom cancel out. We end up with a pi here in front. And now the integral is exactly the same as it was before. That's going to be a 4x minus a 1/3 x cubed. Got it? Being taken from 0 to 2. So volume is going to be pi times, and here we go. Plugging in a 2, 4 times 2 is going to be 8, minus that 8/3 there. That's going to be 16/3, just like it was last time, minus, plugging in that 0 is going to get us 0. And that should give us our answer now, guys, of 16/3 pi cubic units. Okay, that is the answer we just came up with to part B. Now, when we got done with part A a moment ago, I asked you guys, is there a geometric formula that we know that we could use to verify that result of 128/3? And unfortunately, the answer to that was no. But if I ask you the same question right here, if you think about what this three-dimensional solid might look like if you continued to draw semicircles sticking up in the air, kind of looking something like this, we might start to get the sense for what's happening here. This is actually kind of a dome shape, everybody. It's actually going to be a hemisphere. And we know, or at least we should know, how to find the volume of a hemisphere. So let's talk about that real quick. You may have forgotten this formula, and it's no big deal if you did. I promise I won't yell at you. But that's not what I wanted to do. But the formula here for, okay, we're struggling here, Fontana. All right, the formula for the volume of an entire sphere is 4/3 pi r cubed. So the formula for volume of a hemisphere now is going to be half of 4/3 is going to be 2/3 times pi times your radius cubed. Well, in this case, that radius, we've been dealing with this all along, is going to be 2 cubed. So what happens here, guys? 2 cubed is 8. 8 times 2 is 16, and that's going to be 16/3, and the pi just goes along for the ride, cubic units. So, of course, doing it with geometry was a lot easier than the result we got doing it with calculus, but sometimes you won't have that option. Okay, so that one worked out for us there, and not too bad. So, all right. Hopefully we're we're doing all right with this. And I wanted to do one more problem with you guys here in this section when we're building solids on a plane before I stop this video, and eventually we'll move on to the third one. So this one, unfortunately, guys, is totally different than what we've been dealing with before. Now, the base of a solid is the region between two sideways parabolas. X is equal to y squared minus 8, and x is equal to 10 minus y squared. And the cross sections are equilateral triangles perpendicular to the y-axis. Okay, and we got to find the volume of this solid. Boy, this is somebody's idea of a good time. Mine. But anyway, so here we go, guys. We're in the helicopter. We're clearing out some land, and we're pouring a concrete foundation. So this is going to be figure number 1. And then once we get that done, now we're going to draw the goofy three-dimensional version of it right over here for figure number 2. So what are we drawing, guys? The first shape here, x is equal to y squared minus 8. That is a sideways parabola. Because y squared is positive, it's opening in the positive x direction, which means it's going to the right. And that minus 8 is your x-intercept. It's being shifted negative 8 units in the x direction. So the vertex is going to be over here at negative 8. And beyond that, it's a pretty normal sideways parabola. Nope. Okay, so it was looking something like that and like that. The second one, x is equal to 10 minus y squared, is also a sideways parabola, but this one opens in the opposite direction because y squared is negative, and its x-intercept is now a positive 10. So of course I had to make this a little asymmetrical here. There's 10. And this sideways parabola is probably going to look something like this. Okay, guys, and there in the middle of that region, we have the concrete base that we're going to pour. All right, how's that going to look in figure number 2? Not really a whole lot different, you guys. Our x-intercept here of negative 8, it's just that instead of going vertically across the x-axis, it's now going to kind of go at an angle like this, and I think that sideways parabola maybe going to look something like that. Doesn't have to be perfect, you guys. And the second one has an x-intercept of 10, and I thought it was going to hit something like that. So I think this one is going to look maybe something like that. It does not have to be perfect. Do not spend an hour trying to figure out what's going on here, guys. All right, so there's our concrete foundation. What are we doing now? We're going to build cross sections here that are equilateral triangles that are now running perpendicular to the y-axis. So the piece that I'm going to draw here in figure 1 is going to go from one curve to the next. I don't know what happened there. From one curve to, oh boy, I don't like that at all. Okay, one curve to the next, perpendicular to the y-axis, which means that it's running horizontally or parallel to the x-axis. So I'm going to draw the same red segment right over here. But now in figure number 2, let's draw the rest of it. That red segment that we just drew is now the base of an equilateral triangle sticking straight up in the air, looking something like this. And the fact that it's equilateral means that all 3 of those sides have to be congruent to each other. So that red segment that we drew, I'm going to call B, the base of our equilateral triangle. And we have to figure out how to express B in terms of, well, let's talk about this now too, either x or y. And if you look at how this problem is different from the last 2 that we did, here S ran vertically, perpendicular to the x-axis, and this was a dx problem. The same exact thing happened right here. D was running vertically up and down. This was a dx problem as well. But now in this one, with B running horizontally, this is going to be a dy problem. And that means that we've got to try to come up with an expression for B as a function of y. So how do we measure a horizontal line segment? Right minus left. So something moved on me here, and that was kind of weird. That was supposed to go, Huh, that's very odd. I thought that was there, but I think I ran out of space. All right, anyway, we got it. So the question now is, what stops B on the right? And I'm looking right here in figure number 1. B is stopped on the right here by this parabola, everybody. The one that is going to be 10 minus y squared. So that's what stops it on the right, 10 minus y squared, minus what stops B on the left. That would be the other sideways parabola, which is y squared minus 8. And that can be cleaned up just a little bit here, guys. The 10 minus negative 8 is going to make an 18. Minus y squared is a minus 2y squared. So that's how long B is going to be. The next thing we have to do, and this is difficult, is we've got to come up with an expression here for the area of your equilateral triangle. And to do that, all right, guys, I got to promise you, you're not going to see anything this complicated show up on a test, but geometry teacher Mr. Fontana needs to take you back to something here. We're going to talk about how to find the area of an equilateral triangle. All three sides here have to be congruent. We know that. And let's see what's going on. Well, an equilateral triangle has the same area formula as any triangle, guys. 1/2 times its base times its height. But in an equilateral triangle, some interesting things happen. Let's talk about what's going on here. Base is the measurement of the entire bottom side, which means that this little piece right here is going to be base over 2. And if you guys recall, we've got a 60-degree angle here and a 30-degree angle here. This is a 30, 60, 90 triangle. So the height of this triangle here is your short leg, b over 2, multiplied by the square root of 3. Height is b over 2 multiplied by the square root of 3, otherwise known as root 3 over 2 times b. So let me go back to this formula now in blue. Area of an equilateral triangle is 1/2 times its base, but its height can be expressed as root 3 over 2 times b. And what happens now? Area of our equilateral triangle is going to become root 3 over 4, and b times b is going to be b squared. But I should be careful. This formula is only valid for an equilateral triangle. So, to be very clear with you guys, no, I don't think that's something you learned 3 years ago in geometry. So no, I'm not expecting you to have it memorized. And no, I wouldn't ask you to come up with something like this on a quiz or a test. If this type of question did show up, I would give you that formula for the area of an equilateral triangle. But anyway, that's where it is. And wasn't that more fun than me just giving you the formula? You don't know if I'm just making stuff up. So root 3 over 4 times base squared. So let me write that down here. The area of an equilateral triangle is root 3 over 4 times your base squared. And we now know that the base is 18 minus 2y squared. So area, written as a function of y, is going to be root 3 over 4, and your base is 18 minus 2y, and we're squaring 18 minus 2y squared, and then that whole base now gets squared again. That, everybody, is a mess for that function, and there's not really anything that we can do to clean that up. So that is where things stand right now. Okay, but the hard part is done. We have figured out our A of y formula, so now we're ready to go ahead and find our volume. And our, dang gummit, my hand just keeps hitting one thing after another here. So volume is equal to, it's going to be a definite integral now of your A of y formula. So I'm going to bring the root 3 over 4 out in front. The radicand is going to be 18 minus 2y squared squared. We're integrating all of that with respect to y. And the only thing we haven't talked about yet that we now need to figure out is what are your limits of integration, the lowest and highest values of y in this region. So to do that, I better go back to my graph here, and we are trying to figure out, come on, buddy, we are trying to figure out where these graphs cross. So my points of intersection, one of them is going to be right here, one of them is going to be right here. And how do we do that? We take the two functions and set them equal to each other. So we had a 10 minus y squared, and I want to know where that's equal to a y squared minus 8. Okay, I'm going to bring the y's to the right, the constants to the left. I'm going to get an 18 is equal to a 2y squared. We'll divide by 2 on both sides and get a 9 equals y squared. We'll take the square root of both sides and get y equals plus or minus 3. So we could integrate this thing starting right here at negative 3 and ending up here at positive 3. Or we can learn the lesson from the last two problems. It's easier to do this one if we take advantage of the symmetry of that region and just go from 0 to 3 and double it. So I'm going to do that even though this is not going to be an integral that I'm going to do by hand. So I'm going to put a 2 here, and we're going to go from 0 to positive 3 for our limits of integration. Now guys, this integral just looks too complicated to do by hand. I'd have to probably expand the 18 minus 2y squared, and we don't need to spend all night working on that. So it is calculator time, everybody. Let's see what we can do. I think I have my app fired up here. Let's see. Let's not forget the 2 times root 3 over 4 before we do anything else. So 2 multiplied by a fraction, and that fraction is going to be the square root of 3 over 4. Got it. And then we're going to multiply all that by, you guys are going to hit menu, and it's 43 for you guys, I believe. The definite integral starting from 0 and ending at 3. And then our integrand, everybody, let me make sure I've got this right, 18 minus 2y squared, quantity squared. So 18 minus 2y squared, okay, close the parenthesis, quantity squared. And we're integrating all of that with respect to y. And unfortunately, you guys, I really don't have any way to approximate this answer here, so I'm going to go ahead and hit enter and get this answer of 1296 root 3 over 5, or really, probably just need to get in the habit of approximating these here, 448.948. And I'm going to write that down here, 448 point, what was it, 948? It's a lot of digits to remember. 948, yep, that was it. And okay, guys, that is going to be our answer here for the volume of this third solid that we have built on the base. So that is the last thing I wanted to do with you here for video number 2. I've got 2 more things, well really 1 more concept to talk about and 1 example, but I think I'll throw that into the 3rd video. That one should be pretty darn short though. All right guys, hopefully this helps, but we've got to dive into these problems and find out if we know what we're doing or not. So good luck and let me know when you have questions.